Well, good morning, guys. It's a lovely snowy morning here. I figured since I'm doing a base file here for a project we're currently working on, I would take you through it and kind of show you how to set up a MaxxECU. It's a pretty simple setup. It's an RB25 with upgraded injectors and coils, built, bored half a mil over, and basically a stockish turbo. So we're going to be setting up this base map to work with a plug and play adapter. So let's get started. So you can see this is just a base file. This is what you get when you open up the program. I'm going to select a race because that's what it is. Default features, right? That doesn't really matter. So we're going to start at the top and we're going to work our way down. So it is a piston, it is 4-stroke. It is, however, a 6-cylinder. Right? This is all default settings that just come in the base file. And yeah, I can open up a base map and stuff, but I kind of want to take you through setting it up from start to finish so you have an understanding, So we're just going to start top to bottom, like I said. So it's a 6-cylinder. Don't worry about the alarm in the corner. We'll solve that. It's just bitching because we haven't assigned these yet, but we'll work from the top down. So it is 2545. I did a quick search just to see what the displacement would be on an RB25 with a half a mil overbore. So naturally we go, a little bit higher than the 2497 cc's that it is factory. When you're dealing with volumetric efficiency based systems such as the Max, Mtron, Haltech, basically any of them, it's really important to get all of your engine data right. So it's really important to get your displacement and injector data correct so that everything can calculate correctly. Because at the end of the day, you're trying to match fuel with air. So the more accurate everything is, the more reasonable your tables become. So we've got that set. 300 RPM is fine for max cranking. Sometimes I'll be 250. It depends how it starts. It usually doesn't cause a problem. Since this is a common inline 6, it's 1, 5, 3, 6, 2, 4. I've got that memorized as I should. We're going to leave the logging settings for now. I usually finalize that after. So again, we're just working from the top down. This ECU does have Bluetooth abilities, and just to showcase real quick, this is one of my favorite features here is this Bluetooth switch. So what that enables you to do is rather than tying up a physical input, like a digital in or something on the ECU, this allows you to assign a virtual switch in the application. So in the Bluetooth, in the M-Dash application that you get from the Android store, right? So in that app, you can configure everything. So once I've assigned these switches in here, so I could, for example, go boost, right? And then I could have that, change boost. Where is it? Where are you? Where are you, boost? Yeah. So I could have that, for example, set to boost target switch, use table 2, right? So in the app, then you assign that switch as this, it'll automatically assign. You just select that switch and put it on the screen in the app. So when you flip that switch, it will activate this function. So it's pretty handy, pretty good to have. I won't use it for anything right now. So we'll just set that back to no direct function. Firmware, we don't need to do that. Tune notes, I usually kind of put some general information just so I know what I'm looking at. So it's RB25, 0.5 millimeter overbore, ID 1050X injectors, stock-ish turbo, FMIC, front-facing manifold, aftermarket coils, stock CAS for now. So that's kind of generally what we're doing here. This is all just stuff you can set. These are your preferences. You can set your units and stuff. I prefer metric. That's how I work. And to be quite honest, in my opinion, metric is easier. Dealing with Lambda is easier. Dealing with KPA is easier once you understand how KPA works and you can do the conversion in your head. It's just much easier to work with. Update, we don't need to worry about. ECU lock, we don't need to worry about. So next, we're going to jump into limits. So I'm going to set this rev limit at a nice soft 7200 just for now. Default values are good. You can play with this a lot. You can do whatever you want with this. You can make a more poppy limiter, whatever. But for now, that's what we're doing. This is just a startup map. I'm going to enable boost cut. 200 kPa is fine. This is all kind of default values. It's fine. Lean power cut, another one of my favorite features. I enable it. Anything over 130 kPa, which is about 7 pounds, 6 pounds of boost. Minimum RPM, 3000 is fine. That's probably where this thing will spool. Again, these are kind of fine values just to start with. And then I don't really like the fixed value. I like it to actually track the lambda table. So fixed value means if it goes leaner than, like, let's say 0.9, the way it's default set right now, it'll trigger the lean cut and shut everything down until it goes below all of these things. I prefer to be tracking the actual lambda table. So then I'll allow it 0.06 as a start, right? So if you're targeting like 0.8 lambda, which is about 12 flat, 11.9, this will allow it to go to like 12.5 or something like that. Usually I'll do that during tuning, where I'm listening with my knock ears and setting everything up. And then once I have all the closed loop, which we'll get to next, once I have all the closed loop tracking nicely and everything, and I'm in a nice tight spread for my correction, then I'll bring this down to like 0.03 or something. You don't want it to be too invasive, like, sometimes spikes happen, whatever. Sometimes the lambda sensor is slow, but it's kind of like a user feel thing, right? So we're going to go 0.8 seconds, so not quite 1 second, and then 1 second before the cut. And then this basically just means it'll reactivate below 10% TPS. So basically the requirement is that if you hit this lean power cut, you have to get off the TPS and then back on it, right? So then this will also display, if you're using the MTune app, the M-Dash app, it will display on the app a code, and you can actually like check the code and clear the code, but it'll also show it in the program. EGT power cut, we're not using it right now. We're not using EGT sensors. Warnings, again, this is stuff that you can use, but I don't really need it right now. Oil pressure cut is another useful function, but I usually do this after I have things set up. And to be quite honest, I'm not sure if this owner is going to be going with oil pressure safety or not, but I highly recommend it. It is a really good feature to have so that you don't have to watch your gauges all the time. If you're out on the track, you don't want to be staring at a gauge. You want to be driving, right? And so this kind of takes care of it for you. And again, like, I usually set this pretty loose, like if I'm seeing 500 kPa, 550 kPa, which is roughly 75, pounds of oil pressure, I'll set it at like 350, 400 so that it's not too invasive, but so that if there's a serious problem, you are going to see it, right? GPR limiters, these are just all limiters that we can use for whatever function we want. I wouldn't worry too much about those right now. All right, so now we're going to get into fuel. So fuel general, we're VE. We want to be 720 degree. This is just the way that it works, the engine cycle. So a 720 degree cycle is a proper cycle. So your bottom end will do 720 degrees in an engine cycle. Your top will do 360. It's 2 to 1, right? So your valves move at half speed to your engine speed. So a full engine cycle is 720 degrees of crank movement. Okay, so yeah, this is our stoic. We're just running gasoline on this car. If we were running flex fuel, then we would have the sensor enabled, and we would choose flex fuel, and then there's a whole bunch of settings for that, which I can go to on another one. This is kind of handy. These guys actually do the injector characterization, so we can actually just select a 1050 XDS, which is what we're running. 1 injector per output, that's normal. 1 injector per cylinder, that's normal. If you're running, batch fire or whatever, then you could select 2 or 3, depending on how many, right? 3 bar is going to be our fuel pressure, that's fine. If I have a fuel pressure sensor, normally I'll track it with this. And then I will actually, so they do have the data pre-populated in here. Sometimes I'll bring my own data in from the manufacturer and make it a table. But anyways, usually I will use the fuel pressure sensor to track injector flow. So as fuel pressure increases, flow increases. As fuel pressure decreases, flow decreases. So there is a way to track that and have a table for that data. Okay, so back down here, we're going to go end of injection. That's kind of what I'm used to for the injection angle. And then we're just going to select, some fairly basic numbers. And then later on, we actually tune this on the dyno, right? But for now, I basically just selected 400 degrees at idle, 320 degrees. That's where these things like to be, 400-ish degrees at idle. That's, again, for another video that takes playing and messing around, right? So, startup, warm up. This is kind of fine. These are fine default values. I don't really have a problem with these. Warm up enrichment, the same thing. I'll span this a little bit differently. So I'll go up to let's say 100 degrees and I'll leave minus 30. And then I'll just give it a little bit more resolution. Some cars do like some enrichment here. Some don't. It just depends on what you're dealing with. I find that RBs do like a little bit until it's full warm. So we'll have 0 kind of in this area, but then it'll allow us to kind of populate this and use a little bit more. This is basically how much extra fuel it throws at the engine as the engine's warming up from cold, right? Same thing with this. I'm going to rescale this axis because it is possible in our weather, although I doubt anybody drives this car in the winter, but, wrong axis. You can see we're at 0 degrees. Well, what if you're starting below that, right? So we're just going to go minus 20 and still leave it to 100. And then we're going to go 8 just to add a little bit more. Now, I know these things like a lot of fuel at these cold temperatures, so I'm just going to do a multiply function and go 50%. And I'm going to do a multiply here and go 15%. They like a lot of fuel right away, and then it kind of gets out. So this is basically after the initial start. So once you've passed the 300 RPM that was in the startup RPM, once you've surpassed that RPM, the engine is considered running. So then it'll go through the after start enrichment time, which will take you to the 60-second mark. So none of this should be populated at least at 60 seconds. Otherwise, it'll hold on to this as the engine goes into normal running because it'll never expire, right? So you don't want any numbers in here, and then you can interpolate this across, but typically this is what it wants. Typically it could all phase out here. It depends on the engine. Every engine's different, right? Fuel priming, as it says, I don't usually enable this right away. I kind of play with it later. I don't worry about it right now. It's not really necessary. IAT trim, again, this is just a built-in trim that will pull fuel as the intake air temps get high. That can be played with. Usually you don't have to play with it. The fuel model in this is actually really good. Acceleration enrichment, so this is your tip-in. Pretty common. So event-based is recommended, and we're using a mechanical throttle. So if you're using the E-throttle, this is E-throttle position. This is E-throttle target, which would basically be your PPS, or pedal position sensor, or minimum or map, right? But that would only be on a car that, let's say, doesn't have a TPS for some reason. Who wants that, right? So we're going to leave it mechanical TPS. I usually set this to 4, but again, it can change. This is the rate at which the throttle has to move. I find this is a pretty, I'll set it to 20. It's a pretty good start setting. The settings in here are generally good. This is your table. So this is basically your percent per second rate. So if you really smash your throttle hard, you'll access up here. But if you're only doing small movements, you'll be down here. And then this is just RPM, right? So basically this scale is the harder you smash the throttle. So if you go to a 0 to 100% throttle within half a second, you're going to kind of access these cells up here, right? So you want it to be richer. The harder you open the throttle, the more of a gulp of air it's going to take. So you want that fuel to match it. This is pretty good for default. This is just we're at our operating temperatures, we're not adding anything to it. But as an engine is colder, the fuel evaporates more slow as it sprays against the valves until it gets some temperature in the head. And so we need more fuel to offset that, which is why we have a startup, offset right here, right? So this is our startup offset, right? So At negative 30 degrees, we're injecting 54% more fuel over the top base amount of fuel. So it's pretty simple. And then they give you another correction here. That's the cool thing about this, is that they give you lots of flexibility if you need to like tune around things or add more things. Barrel trim, I like to enable. The table is pretty well populated. I don't really mess with it unless I have to. Lambda control, we're using the built-in Lambda controller on this. So we're using a wideband target. Minimum coolant, I like to start low so that the closed loop can take control if there is too much startup enrichment or whatever. Again, minimum runtime 15 seconds. Most of this is fine and can be played with. This is just basically it deactivates on transient throttles so that it doesn't try to pull fuel or add fuel where it shouldn't. Here's your reactivation delay. I like to set this a little bit high. Sometimes I find it meddles. So this is kind of an important setting if you're expecting the closed loop to work at fast engine speeds. So we're just going to rescale this axis real quick to 8,000 just to give it a little bit of over. And then we're going to go 15% here. We're going to go 12% here, 9% here, and then I'm going to interpolate down to 2% here. And this stuff can be played with and stuff, but this is basically the speed at which it does corrections. So at a higher RPM, you're going to need more correction. At a lower RPM, it'll get kind of fiddly, and you don't really want that. So what I'll do here is I'll usually, oh no, why did I do that? So I'll go like -5%. So this is how much it can take away. I don't like to give it too much while I'm tuning, just in case something's goofy, right? We could kind of want it to bottom out and then we watch it. And then I'm just going to interpolate this. And the same thing here. This is maximum positive. We're going to do the same thing. We're going to go like 10%, and then we'll go 15%, and then we'll allow this to there. Okay. So these are, good base settings, right? Fuel adaptation is your long-term fuel trim. We don't have to worry about that right now. We do want overrun cut, so it'll be under 1% TPS or 20 kPa, 24 kPa. So basically, this is when you're off the throttle, coasting in gear, right? It'll shut the injectors off. It saves fuel and keeps it from popping and stuff. So it's definitely something you want if you want the car to be tame. If you want pops and bangs, then you shut it off and retard the timing on decel. So we have a 0.6 second delay. So from the time you go off throttle, it waits half a second before it goes into the decel cut. This is where it will reintroduce fuel. So when you're off the throttle and you're coasting at 2,000 RPM, it'll bring the fuel injectors back online. We don't need EGT correction. We don't need cylinder adjustments right now. Again, this is just fuel usage stuff. This is for mileage and stuff. That's just another feature that it has. All right, let's go into ignition. Okay, so we're not wasted spark. We're coil and plug. We're sequential, meaning that we're firing each coil individually. We're not dual bank, so we're fine. Usually I find this is about 75 microseconds for the system delay. So basically what happens is you lock your timing at, let's say, 10 degrees, and when you're shooting in your timing anyways, that's what this function is for, to synchronize the timing with the engine, with the ECU, right? So you want your timing shown on your balancer to be what we're commanding in the ECU. So if we're commanding 10, we want to see 10, right? If you're like commanding 10 and you're seeing 20, that's a problem. You're 10 degrees more advanced than what your table is saying. So you want apples to apples. You want what you've synchronized with it to be the timing that you see, right? So we'll get to how to set that up in a minute. But yeah, that's basically, so what you do is you rev it while the timing is locked, and if the pointer moves a little bit, then you can apply this ignition system delay, and that'll straighten that out. And then typically you have to move your trigger angle around a little bit until you kind of get these both working together. With a reluctor sensor, like on a 2JZ, this is more like 100 to 120 microseconds. It's just kind of the nature of the beast. But the idea behind this is to make sure that you get no timing drift at all. So when you're at 6,000 RPM, the timing is the same as if it's at 2,000 or 1,000 RPM, right? So this is kind of a feature that we use, but this is also in the trigger setup screen, so I don't really use it right here. Cranking angle is fine. Some engines require more or less than 10 degrees, but I find 10 is a pretty good starting point anyways. These are aftermarket coils, so I'm going to bump this dwell time up to 2.4 just for now. Other than that, the standard settings are pretty good. If you're finding you're getting spark blowout, you can use this to kind of, or not this, sorry. So in your map adjustment, you can use this too for your voltages and stuff, but typically you want like this to reflect this area here. So we've selected 2.4 milliseconds, but down here at 8, it's automatically giving you 150%, or I should say a 50% increase on that, right? So then you'd be more like 3 or something, or 3.2 or something like that, which is normal. Normally you run more dwell, the lower the voltage is. So this is already kind of doing that for you. But let's say you're having some blowout and you know you have a little bit of room on your dwell, then you can use this dwell map adjustment to add some extra percentage of dwell to help, make a hotter spark, right? So that's what dwell does, is dwell makes a hotter spark. So dwell is the time from when you've initiated the spark, so when you've asked the coil to start saturating, to when the field is dropped and the coil provides a spark. So that is your dwell time. So the longer the field is active, the more charge builds up, and then when it's released, the more spark there is. But you have to know what the dwell settings are for your coils. So if you don't have any more dwell to have, some coils will do nothing, some will misfire, and some, like GMLS coils, will actually dump the spark, which can be really dangerous if you overdwell them, which can result in knock and pre-ignition. You don't want that. So like with those, usually I draw my line, even though some guys run those coils at 5 milliseconds, I draw my line at like 3.8. And usually that's enough to support 500 or 600 horsepower on ethanol typically. So you don't really need a whole lot more than that. Here's the ignition correction. So this is just kind of a general correction for intake air temp and coolant. So you can see here, like once we start approaching 67 degrees, which is 60, 70, which is kind of the danger zone in IATs, like I like to be here, and then it's adding a little bit here. I'll usually like reduce this just because I don't really want it adding, timing. So, but I mean, you're not going to be out revving the piss out of it and driving it here anyways, right? This is negative 20 degrees. So this is kind of our operating area where we don't really want it adding or subtracting. And then this is kind of the danger zone where like we're getting hot, your IATs are getting hot. And so you want to start pulling timing. Some engines are more knocky than others. And so this is kind of like a table that gets tuned during tuning. So if I find that the car is reacting in a way where it's knocking more when the IATs climb up, then I will purposely make this table much lower because this is, better than blowing the engine, right? Even though we're running knock control, things can still get out of control really quickly. So it's important to kind of pay attention to this table. Okay, so this ECU has the ability to control idle via spark and air. And so we allow it to control via the idle control system. So this max TPS means everything under 1%, it can be active. This is fine for a start RPM. This is max RPM. We're going to give it -5 as a maximum retard, and we're going to give it 20 as a maximum advance. So this will work in conjunction with the idle control motor or idle control valve to keep a stable idle. Typically, ignition control is much faster and a much better way of controlling idle, so this is why they always use this setting typically over air. But this will use both. We don't really need this cylinder angle trim. I will use this. And so I use tables. So typically what we use this for is if we find that during tuning there are more sensitive tables than others, then we can actually individually remove timing from each cylinder at any given moment. And so what I'll do is I'll make this like, let's say, I don't know, I want it to start at 100 kVA because we don't really care about everything in part throttle. You're not going to knock in part throttle. And we'll say 250 is the highest value. That's, we're probably going to boost to like 210. So 250 kPa is roughly 22 pounds of boost. I don't think we're going to be there on this one. We're going to change the number of cells to 6. So So that allows us a fairly broad range, right? And then RPM, we'll go to 7,500. 8,000 is fine. And then we'll just change the number of cells to like 8. Yeah, so we get a cell division every 1,000 RPM, right? So this is good. So now a cool function of this is that here's our cylinder 1 offset. Notice how the rest aren't populated. Well, we can just go copy X and Y axis. Then we can load it in. So then we can import. Yes, it always gives you this warning. I'm going import. Yes, so this is basically just copying over the axes of that other table that we've set. So we just got to say yes on every single one. I wish you could set that so that you didn't have to do that, but whatever. And here's cylinder 6. Okay, knock sensors. We are using knock sensors. We are using upgraded Bosch knock sensors. 86.5. I don't know if it's that granular, but so sensor 1 will be cylinders 1, 2, 8. Cylinders 1, 2, and 3. Sensor 2 will be cylinders 2, 3, and 4. Or sorry, 4, 5, 6. What am I doing? I need my coffee. Yeah, and then we can enable this if we need to. It just depends on what it's doing. Sometimes it'll be useful to adjust this for the localization of the sensor. So on an RB, for example, the sensor is in between cylinders 2 and 3. So you could, if you needed to, depending on how noisy it is, you could take cylinder 2 and 3 down to like 80% if you find that they're the only noisy ones and that you're not hearing any knock in your knock ears. You could bring those down to kind of normalize them with the rest, because obviously being in the close vicinity of those two cylinders, they're going to experience more noise, right? So that's where this is useful. I usually do that if I start seeing things be weird, right? Again, this is tuning. In the tuning, this is your knock sensitivity. So any number of knock fast over this will result in it thinking that it's knock. So this, again, you will log knock during a pull, maybe a low timing pull, and then you'll set this table above it. And then so anything above this number is considered knock. It varies from engine to engine. Then we get over here, if we enable it, which I don't have it enabled yet. So we enable trim table. So this is the maximum amount of retard. I don't like to go that high. I usually like 10 degrees, and then I'll work my way up there. Usually that's more than enough. So this is the retard step size. So this is how many degrees per knock event it'll pull out of that given table or that given cylinder. This is the advance. So this is how quickly it'll put it back in once it's done. And then this is just a live table that will show you, if it's trimming or not. So usually I'll do a pull and then I'll jump over here and see if any of this has populated itself. So you want this to be realistic to what you're doing, right? So again, let's say 100 kPa. No, let's go 40 just in case, right? So now we have a realistic number here. And then we want to edit this axis because we're going to be revving higher than that. So let's just set it at 8,000, even though we're going to be like 7,500. Let's set minimum RPM at 1,500. So that's a pretty good sweep. So then this will populate, right? And this will become a trim. And then this, as it sees that there's no knock, will actually pull the numbers back out of this. So you may see numbers going in, but then you'll see numbers coming out if it's determining that it's not knocking anymore, right? So, okay, idle control. So we're going to be running open loop just to start up. Actually, no, we're going to be running closed loop, dual mode, air, and ignition. We'll make the cranking duty 80% for now. After start time, 1.5 seconds. This is just how much time it'll hold this 80% after it starts up before it drops out. Usually these are a little bit higher. So I'll just interpolate this down. Usually at idle we're 45 to 50%. So I'll just kind of interpolate that just for now. Again, this is just settings to start with, right? AC idle up, that's fine. I don't even think this car has AC. Clutch idle up, rad fan idle up. This is if you're controlling your fans. Some of this is irrelevant. Some of this gets tuned. This is our control deadband. So anything more than 25 RPM error, the system will try and resolve the error. Anything less than that, it'll just let it go. So if you're targeting 800 and you're at 823, it won't try to do anything. But as soon as you're at like 830 or whatever, it'll start trying to control the system again. It'll try to bring the idle down, right? This is usually fine over TPS 1%, just so we allow it a little error. Speed is kind of irrelevant. Minimum coolant, this is for closed loop, so 0 degrees, right? That's fine. Usually I like a ramp down time, so this will hold a higher duty when you get off the throttle, just to bring the idle down smoother. These settings are all fine for now. Again, this is stuff that gets tuned, right? Here's our target. This is fine, so this is the target for the closed loop system. So we won't get into boost control yet. We don't really care about motorsport. This is all off by default. Speed and gear, again, off by default. So now we're going to work over to our inputs. So that's a summary. They've actually changed this a little bit. I haven't actually played with this. That's pretty cool. Okay, so we can start from the top. There's our inputs. We know what all of this is. Yeah, okay. So we can start with trigger. So we know this is a digital, just because that's the way Nissan does it. It's going to be rising. Home sensor is also going to be digital. That's also going to be rising. And we're going to select the Nissan trigger pattern, Nissan Cast version 2. That should be a good default window size. There is a way to do it. It's all in the help files. But what I'm going to do is I'm going to jump over to another map I have open and just grab their settings. So all I care about really is this. So it's 58 degrees is the default. So we're just going to set that. Again, this is our setting that we set when we're shooting our timing in. So the easiest way to do this is have your timing light right, all timing lights or most timing lights. I haven't seen one yet. I wish somebody would make one that has like a trigger input instead of having to use the inductive lead. Maybe they do. Let me know in the comments if they do. But the way to do this is to pop your number 1 cylinder cast out, take an old spark plug wire, like from a distributor system or whatever, jam the bare wire end into your coil, like where the spark plug would normally sit, put the other end on your plug, then connect your inductive lead there, and then you can have a proper timing light working on a coil unplug engine. So basically what you'll do is you'll lock the ignition angle, let's say at 10 degrees. So if we've locked the angle at 10 degrees here, we want to see 10 degrees at the balancer. If we don't, then we move this value until we do, provided that your cast is centered. Usually I'll just leave the cast in the dead center, and then I will adjust this value until it's where I want it, until it doesn't, until it matches this number, right? And then we're good. Then you can unlock it. You don't want to leave that locked. It will actually flash up in the corner here that it's locked. So temperature sensor, we're not going to be using a Bosch. We're going to be using we're using a GM IAT, right? So same calibration. I use the 1/8 motorsport sensors from, oh my God, who do I use this from? Anyways, it's a 1/8 thread motorsport sensor, but it still uses a GM IAT calibration. So it's basically the exact same thing. The coolant sensor, the Nissans just use basically a Bosch NTC. It's just a regular sensor, so it's fine. Down here, we will typically, with the ECU, with everything turned on, you will have your foot off the throttle and you'll go get current voltage. Then you'll mash the throttle to 100% and then get current voltage. And then this will span your throttle so that it's correct. Lambda sensor, we're using a single sensor. We're using the internal controller, which is great to have on these. It'll start the warm-up process at engine startup. That's fine. And it'll shut down 120 seconds after. So since we're not banked here, each cylinder is going to use lambda sensor A. So if we had a bank setup, like let's say a V6, then we could select 2 sensors, right? And then where bank 1 and bank 2 is, and then have A, B, C, whatever, or A, B, A, B, A, B, right, for your bank. So in this case, it's an inline 6. It's all in one bank. It's fine. We don't have EGT sensors. Digital inputs. So these can be used for like switches and stuff, or you'll run your ethanol sensor into this if you're running an ethanol sensor. I think I'm going to be using this for speed. I'm just going to have a look at my other map just to see how they've defined it. I could have just used this map for a base file, but I really prefer to go through the entire base map as I'm making a base map for in-vehicle, because sometimes you can miss settings. So this is a way of me forcing myself to go top to bottom and not take any shortcuts, right? So yeah, we're using that as VSS DIN 1. That's just how the plug and play is configured. The Nissans do actually feed a signal from the speed sensor over to there. So we can just go down here. Vehicle speed sensor simple. And I believe it is active low. Is it active low? Let's find out. I can't remember. Active high, 5 volt pull up. Okay. So go back, active high. Okay, so that's set up for now. That's good. Then typically what I'll do, I don't really use these two, although these two you can use for switches and stuff. It's kind of handy, but they're kind of made for temp sensors, so you can add like additional temp sensors. But what I'll do here is I'll make analog in 3 fuel pressure sensor 1, and then so I have the calibration memorized. So basically, it's 1034 at 4.5, 0 at half a volt, right? So that will span this. So now we're span 4.5 volts, 1034 kPa, which is 150 psi, down to 0 at 0.5. And then our unit is kPa. And then this one I'll usually set as oil pressure. So I still have to, I have to configure the plug and play unit right now. So usually what I'll do is I'll define my base map first, and then I'll print that configuration and make everything match at the base harness. So what they give you is a plug and play harness that interfaces with the factory ECU header, but then they give you an auxiliary harness that comes off of that you can pin and populate yourself. So it's typically populated for a couple of analogs, your wideband sensor, which the ECU runs. So typically I'll move those around to match whatever I have on my setup. So in this case, I'm going to add to that side harness, as I call it. It's basically going to be running IAT, because Nissans don't have IATs. They have MAFs, which don't have IATs. So we have to add an IAT. Oil pressure, fuel pressure, and lambda sensor. So those are usually the things that I add by default. Even if I don't run an oil or fuel pressure sensor on the vehicle, I will still add those as a default. Yeah, so engine oil pressure. This one's a tricky one. It's not under O, it's under E. Oh, maybe it is under O. Where are you, oil pressure sensor? People are probably yelling at me right now. Here we go. Okay. So we like to use, just to keep it less complicated, we like to use the same sensor. So we'll use the same 150 psi sensor on this, which is 134 kPa. So again, 2-point calibration. It automatically, nope, never mind. 0 and 1034 at 4.5. Boom, we're calibrated, and that one is also in kPa. And then you can offset it if you find it's reading weird, but I've never had one read weird. You can see that the rest of these are for, typically we use the rest of these, so AN5 through AN8 are used for drive-by-wire. So you'll have your pedal position sensor 1, pedal position sensor 2, TPS sensor 1, TPS sensor 2. They have redundancy built in, right? So that's, if you're using drive-by-wire, you usually use those. If not, these can be used to bring in any sensor, any 5-volt sensor. So whatever you want. Okay, so that covers inputs. So now we'll go to outputs. So output config. So now we'll have to consult back to our base map just to see how they've configured the outputs. So GPO1 always on. So this one is the ECCS relay. So this just automatically turns that ECCS relay on. If you don't turn it on, then you're not going to have your CAS working or your injectors working because they run on that. So GPO1 we'll set to always on. So that's no problem, always on. And then we'll bounce back. We'll just do this one at a time. So GPO out 3 is default configured to idle PWM. That's our idle valve. So we'll go back here to GPO out 3 and we can actually search idle PWM solenoid or idle valve. Again, we'll just consult this one. I just like to go back and forth. Here's your VCT. So this controls the variable cam on the RB25s. So GPO 4 is VCT. So we'll set that, and that takes a little bit of extra settings. I'll show you. User. So that's going to be a user output on user output 1, which is on GPO output 4. Then we go down here to user output 1, and so we'll call it VCT cam, right? And then so typically these will operate when your RPM on this engine is greater than 1500 RPM. And well, I actually like to use 3, A, N, B, and C, and I'll show you why. So then we'll call this one RPM. So we're doing it greater than 1500 and less than 5000. So typically you run these engines with the stock cam and everything in between. You want your, because this is not variable, it's just an on-off type deal. You want to turn it on at around 1500 RPM. That's where it gives you your torque in the mid-range. Turn it off at around 5000 RPM when you want to bring the torque back, like allow it to come back in, right? And then, so I don't like it getting overactive, so I'll usually set this one too to where, throttle position. So where throttle position is like, let's say greater than, 4%, let's say, right? So this will not turn on unless the throttle percent is more than 4%, more than 1500 RPM, but less than 5000 RPM. So on a dyno pole, once we mash it, that's satisfied. Once we hit 1500 RPM, that's satisfied. It will be active. Then once it hits 5000 RPM, it'll turn itself off. We don't want to flash. This actually bit me in the butt one time where it was like making weird dyno stuff when I was learning this thing, and it made the dyno wobble because it was turning the VCT on and off. It was super weird. I didn't realize they had that as a default setting. So normal, no output flash. We don't want it doing that. Okay, I'll back out to output config. So we're up to number 4. Let's see what they have here. 5 is check engine light, and 6 is fuel pump relay. So 5 is check engine, and 6 is fuel pump relay. They make it pretty intuitive. It's pretty easy to set this up, right? So 6 was fuel pump relay. 7 is boost solenoid, so that will control, in this case, with the jumper harness, the RB25 has a factory solenoid. So this will just control that wiring to that solenoid. So, so 7 will be boost solenoid, 8 will be tack output. So we'll go over here, boost. We're going to do closed loop. This is by default tack, so we'll make it tack. 9 is going to be lambda heater because that's by default. Lambda sensor 1 heater, so that will modulate the ground to the sensor and make the heating element run. And then the rest are disabled in this particular thing, right? And then you can see our extra injectors and extra ignition are disabled. You can use injectors as spare outputs, so you can run fans and stuff with them if you want. But we do still have a few of these left too. You would tie one of these H bridges up as your drive-by-wire. This is what actually runs the DC motor on the drive-by-wire. But you'll still have these extra, and you'll have these extra. And the cool thing about these is that you see where it says 12-volt driving. So if I wanted to, I could actually just run one wire from the ECU to the boost control solenoid and then ground the other side, just as an example. Or even for the VCT sensor, and this would drive it. I think they said it'll do up to about 5 amps, which is more than enough to drive any solenoid. So that's kind of handy, is to have those two that actually run a 12 volt high output. I think you could use that to run a 12 volt coil as well. So definitely handy. But we'll just go over here and we'll clean this map up. We'll make sure that this is not enabled, because we don't need this enabled. We're not using them. Same thing with ignition out. 7 we're not using. 8 we're not using. Yeah, so then idle PWM solenoid. I know these are around 150 hertz. Tac output, this stuff can be set as you run it, but this should be fine as a, I think this needs to be 3 on those. I can't actually remember, but I usually just set it up as I'm doing it. This is just your RPM sweep, so when you turn the ECU on, it'll sweep RPM. So you can actually do it to a set RPM. Let's say you don't want to bottom out your tac, you can do it to like 6,500, whatever. This allows you to calibrate any error in the tachometer, so you can do a single value or a table. It's pretty handy. We've already configured that, so that's cool. So diagnostics. We don't really need to do anything. Oh, why is it showing that? Okay, here we go. So this is where your error codes will pop up. You can test your injector and ignition output test. This is usually my first thing I do before I start the engine, so you can actually trigger each injector manually. You can have it do a pulse, whatever, right? You can shut cylinders off if you're trying to like find a misfire or something. So instead of manually unplugging injectors, you can actually just do this. So ideally, if you have like a misfire, the one that you shut off won't have any effect. So like, let's say you have a misfire on 4, right? If you shut off 1, it'll stutter more. Shut off 2, it'll stutter more. Shut off 3, it'll stutter more. Shut off 4, it'll be no change, right? That's when you know that your misfire is on that cylinder. So that's handy. Injector resistance, you can have it measure. So key on, engine off, you can run this test and it'll tell you the resistance of your injector coils. Just good to know whether they're a high impedance or a low impedance injector. If I remember correctly, the MaxxECU Race only, the Race and Pro, and their new ECU have the ability to run both high and low impedance injectors, and then the lower models can only run high impedance injectors, which is kind of most ECUs out there. Trigger logger is handy if you're having issues with your trigger. This will show you where and how. Oscilloscope is kind of the same thing, even more useful data, so you can see your crank and cam signal and see where the dropouts are, as well as see where the what the voltages are looking like, so you can set your thresholds, right? And the tune problems, that's just more stuff. Okay, so fuel table. By default, it's not bad. Like, it's fairly decent. I do typically bring over a table from another map just to assist me in being quicker, and then I'll quite often just trim that, but we'll just start with this. So we want to give this resolution up to 250 kPa, just in case. We'll give it 13, give it a resolution of 13. We want to go and rescale this axis so that we're up to like 8,000, even though we'll probably be like 7,700. That should be fine for resolution. 500 RPM. You can kind of go from there if you want. This is gonna be your idle area. So I mean, we're gonna set this to like 45. This will probably be rich. So what I'm gonna do is I'm just gonna minus 5%. I just don't want it going too rich. And then what I can do is I can, so we can go over to 3D, and I can actually use the smooth function just to kind of get this looking a little nicer and give me a better starting point, right? Same thing here. We can just do that. We can smooth everything out. This is just a good point to start, right? It's not right. I'm not saying it's right. We can fix this a little bit. Right, and then we can go back to 2D. These will be kind of common idle values. I like to run the lambda right at first startup, so it'll immediately start pulling it out. If it is too rich, this may well be too rich. Typically, these idle in the 40 to 50% range, and can be anywhere from like 90 to 105% volumetric efficiency, typically right here, right? So again, this is like an untuned table. This is just a startup map to get us going, right? Lambda table, same thing. Like up here, you know, I'm gonna want, you know, like 0.78 if I'm that kind of boost. In here, I'm gonna want 0.80 here, and then what I can do is I can interpolate this down. So then, you know, we can be a little bit lean in this area where we're kind of trying to spool up, and then maybe we'll, you know, take a little bit out. I always start on the rich side just to make sure that it's gonna, you know, be good. Yeah, so that's kind of that. That's never gonna really look good just because you're changing targets and stuff. Typically here we can be one lambda is 14.7 to 1 AFR. And then we can be 1 here, and then we can be like, you know, we definitely want more fuel here. So past 4,500, we'll just horizontally interpolate it. So it will progressively get richer in this area. I mean, you're never going to be here. Like typically you're going to be in this area, right? Basically this is all boost, and everything under this is vacuum. So typically you would be cruising, you know, let's say you're on the highway, you're going to be about here, right? Between 40 and 60 kPa, which is vacuum. So you're going to want like 1 lambda. And then as you go to 4,500, 5,000, you're going to need that additional cooling. So you're just going to want to make it a little bit richer, right? This is a pretty decent start table. Like I don't really have a problem with this table. I'll probably pull a few degrees out. As I said, I'm probably going to bring over settings from my other tables anyways, because I do have a few pre-populated maps. But this would be fairly close, provided that you have your base angle set correctly and everything. So we'll just smooth that. And yeah, smooth it. And we'll kind of take this edge out like this. This would run fine on the street. So we're just going to smooth that out. I'm probably going to take this decel area down a little bit. There we go. Let's have a look. And then we can just do this. Oh, come on now. Oh, it doesn't want to go. Hey, why are you like this? There we go. So that would be a fairly functional startup map. I wouldn't be boosting this thing around, but like, you know, we're running a peak timing of 23 degrees at like 5 PSI of boost. So you're probably pretty safe there. That's pretty close to a stock map, but don't take it from me. That's, you know, I'm running knock ears and knock equipment. I'm listening while I'm tuning. That's pretty much it for that. And then as a little added touch, I like to change the target. So this is cool. You can actually use all these fuel tables and ignition tables for whatever you want. So in the case of like, let's say a water meth kit, right? So when the water meth is on, ideally you're going to want to pull fuel out. Okay? If you're injecting enough water meth, you're going to be about half a point away from your lambda target. So if your original target was like, let's say 12.0, then you know you're injecting enough meth when you're around 11.5, right? But because you're using the methanol as fuel and octane increase, methanol has a very high octane level, right? That's why we use water methanol to help keep the knock away and to cool the cylinders. So what we can then do is we can set one of these tables up so that when the meth system is active, when the meth comes on, we can take out that extra fuel. So that basically the idea with water meth, just as a primary example, is that you want to spray so that you go about half a point richer than your target, and then you want to pull that fuel back out so that you get back to your target. So now you're using the water meth, the methanol and the water meth as a fuel. Typically, if you don't pull it back out, then you'll be running in a rich condition and you'll actually lose power. So if you're spraying meth on like a factory ECU'd car and you're spraying a lot of it, you're probably not gaining, you're probably losing. So just good to know that you have to tune that. And the same thing with an extra ignition table is typically water meth will increase the ability to take timing because it moves the knock threshold up due to the increased octane and cylinder cooling. So then what we'll do is, again, I'll make this table only active when the DIN is active, right? Like let's say I'll use a digital input for when the water methanol system is on. So when the system is on, it'll jump over to this table, and then I'll just put extra timing, like when the methanol is active, right? And then when you shut it off, then it just goes back to the normal tables. But anyways, fuel table, I like to add a cold enrichment so that basically it changes the lambda target. So what we do then is we rescale this axis to, change axis source. So we're going to change that to temp, coolant temp, right? And then we're going to go -20 up to, let's say, 80. And so what this will do is we can multiply to lambda table. So if I go, let's say 95%, that means that the lambda target will be 5% richer when it's cold, right? So this allows me to run closed loop even when the engine is at cold temperatures, and it will actually pull any extra fuel out, but still enrich because we're still targeting a richer mixture, right? And then basically we want to be, 100 by the time we hit here, so it doesn't interfere, right? So we can just, again, vertically interpolate that. So, you'll get like 5% more, and then as the engine warms up, it'll fade out. Pretty simple. Yeah, so hopefully you found that handy. Yeah, sorry, no face cam this time. I'm still working on my OBS on this computer and everything. But it's kind of a dreary day. I probably don't look good anyways. But yeah, if you have any questions, concerns, pop it in the comments. Hopefully you find this useful. I think the next one I'm going to bring up is probably Mtron. That's, much more complicated. And I think a lot of people could benefit from at least being able to work out a startup. So we'll get to that one next. I guess we'll see you all on the flip side. Thanks for watching.